Ready? Let's learn some math. Math, 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 math. Math, 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 math. Math, 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 math.
Come, take a journey with us each Monday from 5:30 p.m. on ABS TV. Let's get to the heart of the matter. Math matters. Welcome back to another episode of Math Matters. I'm your presenter, Mrs. Tisha Hughes Thornhill, and today we are going to be taking a look at geometry, more specifically, transformation geometry. As you know, we begin by revisiting the challenge question from the previous episode, and last week we looked at quadratic graphs. When we take a look at the first part of the question, where we are to complete the table, we notice that there are 3 blank spots. So these are the areas that we're going to be focusing on. So the first value is -3. And so the first thing we're going to do is to rewrite the equation. And remember that instead of it saying y, it could also be f of x or f of the particular value that we're going to be substituting in. And so wherever we see x, we are going to replace x with -3. So we're going to have equal -3 to the power of 2, or -3 squared, plus 2 times -3 minus 3. We're going to take it in portions, and so -3 squared is the same as -3 times -3, and that equals 9. Then we have plus 2 times -3. And we'll remember that a positive times a negative is equal to a negative. And 2 times 3 is 6, and so that'll be -6. And then we'll just rewrite the -3. And so now what we have is 9 minus 6 minus 3, and that equals 0. Because 9 minus 6 is 3, and 3 minus 3 is 0. All right? So the second value, which is 0, we're going to do a similar thing. So we begin again with the function, and everywhere we see x, we are going to put 0. So 0 squared plus 2 times 0 minus 3. 0 squared is just 0. 2 times 0 is 0, and minus 3. 0 plus 0 minus 3 gives us -3. And our final value, which is 2, we are going to have 2 squared plus 2 times 2 minus 3. And of course, 2 squared is the same as 2 times 2, so that's 4, plus 4 again, because we have 2 times 2, minus 3. 4 plus 4 is 8, and 8 minus 3 is 5. And so all we'll do is to just place those values into their respective places onto the table. Part B says, using the ordered pairs, draw the graph of y equals x squared plus 2x minus 3. And what we have here is the table from the previous slide, and it is completed for us. And we know that coordinates are x, comma, y. And so our first set of ordered pairs are going to be -4 and 5. Then we'll have -3, 0, -2, -3, and so on and so forth. And so the coordinates would be as follows. So our job now is to plot those points onto our graph. But how do we do that? Well, negative 4, 5, keeping in mind that the first value represents the x and the second one represents the y. And so we need to go onto our graph and find negative 4 on our x-axis. And negative 4 is here. And then it tells us we need to find 5 on the y, which is here. And so we would connect until they meet, which therefore means our first point, negative 4, 5, would be in this spot. Continuing, negative 3, 0, negative 3 on the x, 0 on the y, which means that we're not going to be moving from this position. So our second coordinate goes here. Negative 2, negative 3, negative 2 on the x, negative 3 on the y, and so this is the location of our next coordinate. Negative 1, negative 4, negative 1 on the x, negative 4 on the y, and that is our coordinate. And we continue following the same idea, finding the position on the x first and then the y. Our next coordinate is 0, negative 3. And so that means we're at 0 on the x-axis and negative 3 on the y. 1, 0, 1 on the x, and it says 0 on the y, which therefore means we do not move. And finally, 2, 5, 2 on the x-axis, and then 5 on the y. And so this is going to be the location of our final point. The only thing left to do now is to connect our points using our pen. Try to make a smooth as best as we can. This is not a very good example. But we will connect the points as best as we can. I promise you, I'll do that again and it'll look much better. And so here we are. Patsy asked us to state the following: the coordinates of the x-intercepts, the coordinate of the y-intercept. So let's start with point 1, the coordinates of the x-intercepts. This just means where our graph cuts the x-axis, okay? And so, reading from left to right, we'll notice that this is the first point where our graph cuts the x-axis. Well, what coordinate is that? Remember, we start with the x value, and this would be negative 3. And since the point is on the x-axis, that means our y value is 0. And so that point would then be negative 3, 0. The second location where our graph cuts the x-axis is in this area. And we know that that is 1 on our x-axis. And so that coordinate would now be 1, 0. Part 2, the coordinate of the y-axis, the y-intercept. And so, of course, that is therefore where our graph cuts the y-axis, which happens in this location here. And so that is going to be 0 on the x and negative 3 on the y, which therefore means our coordinate is 0, negative 3. Part 3, the equation of the axis of symmetry. So it means that we're going to need to have our equal sign, and symmetry meaning where's the exact half of this graph? So where's the middle? So the middle here we identify as the line x equals -1. But how do we know that that's the name of the line? It is x equals -1 because no matter which point I choose on this line, x is always going to be equal to -1. And so if I choose this spot here, for example, this point would be located at -1, 1. How about this point? -1, 4. And so the equation of our axis of symmetry is x equals -1. And finally, the coordinates of the turning point. And I think that's clear to see from the diagram where the turning point is. And that's down here, the lowest point here. Okay? And this point is -1, -4. Now that wasn't so bad, was it? Thank you so much to all who continue to email their submissions. Special shout out to one Miss Britannia Bucknell for her consistent submissions. Before we dive into our lesson on transformation geometry, let's hear a word from our sponsor.
Some math. Math, 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 math. Math, 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 math. Math, 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 math.
Come, take a journey with us each Monday from 5:30 p.m. on ABS TV. Let's get to the heart of the matter. Math matters. Matters.
Add and subtract, come and sing with me. Math is life, math is fun. Math matters.
Welcome back, and let's begin. So what is a transformation? Transformations in math involve changing a shape's position or size, or which way the shape points. There are 4 types of transformations. Translations, which involve moving the shape. Reflections, which involves flipping the shape like a mirror image. Rotations, turning the shape. And enlargement, which is when scale factors increase or decrease the size of a shape. We see, participate, and interact with transformations every day. For this lesson, we will focus only on translations and reflections. But before we get to those, let's take a look at some real-world examples of rotations and enlargements. Have you ever been to an amusement park or saw a Ferris wheel or even a merry-go-round? How about a spiral staircase? Well, these are some examples of rotation. In times past, we used to see windmills around, but with the advancement of technology, we can now see wind turbines. These are also examples of rotations around us. When we enter a bright space, our pupils get smaller. And when we enter a dark space, they get larger. This is a perfect example of an enlargement or dilation. Here we see 2 other examples of enlargements. When we go to a photo studio, we have choices of the size photo we would like, but even though the size may be altered, the image itself remains the same. How about when we go to our favorite chicken spot? You know where I'm talking, KFC. We have a choice in the size drink we'd like. There are so many other examples of rotation and enlargement around us. So as you go through the rest of your week, try to see if you can identify more examples. Let's pause for a moment And when we return, we will dive into the focus of our lesson, translations and reflections.
Math, math. Math, 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 math. Math, 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 math.
Come, take a journey with us each Monday from 5:30 p.m. on ABS TV. Let's get to the heart of the matter. Math matters.
Come and sing with me. Math is life, math is fun. Math matters.
Welcome back. Now let's take a look at translations. Machinery such as escalators, as seen on the screen, elevators, a moving car, or even walking are some examples of what we would call a translation. This man is seen engaged in fitness training, battling ropes. Not only are the ropes translating, but the man himself is as well. He's traveling from side to side. So what is a translation? A translation is moving or sliding an image, object, or figure in straight lines without changing its shape. Note that all points of the shape move the same distance and same direction. So what does any of this even mean? So on the screen, we can see what is called a column vector with letters X and Y. And of course, these have to do with the coordinate plane, the axis. So we're talking about the x-axis and the y-axis, sorry. When describing a translation, we must state the column vector. But what is a vector? A vector is a quantity having direction as well as magnitude, especially determining the position of one point in space relative to another. So, in essence, a vector tells us exactly how to move. A column vector takes the form we see. The first value is the x value, which tells us how many places left or right. When the value is negative, we move to the left. When the value is positive, we move to the right. And likewise similarly, I should say, for the y-axis, this tells us how many places up or down the object should move. We move up when the value is positive, and we move down when the value is negative. If we take a look at the graph, we can see two similar triangles, triangle A and triangle B. Triangle A is what we would call the object, and it is mapped onto its image, which is triangle B. So in describing this translation, we would say the object was translated. Well, let's see. How do we know? It moved left, and then it moved up. But how many places left did it travel, and how many places upward did it travel? So what we would need to do is to select a point, any point on the triangle, for example. And we're going to count spaces. 1, 2, 3, 4, 5. So that traveled 5 places left, and 1, 2, 3, 4, 5, 6 places upwards. Therefore, that translation, if we were to describe it as a position vector, would be written as negative 5, 6, because the triangle would have traveled 5 places left and 6 places upward. Here we have another example, triangle ABC. Triangle ABC is mapped onto triangle A prime, B prime, C prime by a translation 4, 2. This question wants us to draw the image, which is A prime, B prime, C prime, and write its coordinates. And so, for every point, point A, point B, point C, we are going to translate each of those points. So let's begin with point A. The translation vector, the column vector, asks us to translate this triangle 4, 2, which means we are going to travel 4 places to the right and 2 places up. So let's do that. 1, 2, 3, 4, and upwards 1, 2, which means A prime is going to be in that position. What position is that? Well, remember we read the x value first and then the y value. And this is located at 5, 5. So A prime, its coordinate would be 5, 5. Let's move on to B. B, moving right 4, 1, 2, 3, 4, and then upwards 2, 1, 2, puts us in this position here. So that point is now called B prime. And its coordinate is, well, 5, 4. Point C, 1, 2, 3, 4 places right, and 1, 2, 2 places up. Puts our point or coordinate at that location, which would be 6, 4. And then we would just connect our points, creating our image. Here's another example. We have 2 triangles on the screen, A, B, C once again, A prime, B prime, and C prime. This question wants to know what is the translation by which ABC is mapped onto A prime, B prime, C prime. So let's see. First, it would be moving to the right. And so if we count 1, 2, 3, 4, 5, 6 places to the right, and it moves downward. 1, 2, 3, 4 places down. And so, since we went to the right and down, our x value is going to be positive and our y value is going to be negative, which therefore gives us a position vector 6, negative 4. We'll be right back after this short break.
Come, take a journey with us each Monday from 5:30 p.m. on ABS TV. Let's get to the heart of the matter. Math matters.
Welcome back. Let's explore our second transformation, reflection. When we look into a mirror, we see our reflection. The mirror between us and our image is what allows us to see our reflection. Have you ever taken notice of what happens to your image when you step closer or further away from the mirror? Well, your image is always the same distance away from the mirror, and it will be flipped, or what we like to call a mirror image. Other than an actual mirror or some form of glass, water can also show reflections. In this case, the water would serve as the mirror. What would be a mirror on a graph? Well, on a graph, a straight line would be the mirror line, whether vertical, horizontal, or diagonal. The object and its image must be the same distance away from the mirror line. Here we have two triangles, a blue triangle and a purple triangle. Triangle ABC is the object and its image is triangle A prime, B prime, C prime. And all we're focused on here is identifying the mirror line. Well, we've mentioned it before. The object and the image must both be equidistant away from the mirror line. And so when we look at our graph, the location of point B, for example, in relation to B prime, or this area here is where we would consider the mirror to be. And that line actually has a name, and it is x equals -1. Hopefully you remember that from previous discussions. Whenever we are describing a reflection, we will need to state the mirror line. So this is important. We can't describe a reflection without its mirror line. So here's another example. Given triangle ABC, draw its image A prime, B prime, C prime when ABC is reflected over the line y equals 0. What are the coordinates of the image? So first, we'd have to identify where the mirror line is located. And the mirror line is identified as y equals 0. We know that this location is the point 0, 0. And every or any position chosen, y is still going to be 0 along the x-axis. And so the x-axis is known as the line y equals 0. So now that we have our mirror line, let's reflect triangle ABC over this mirror line. We'll have to choose each point and count how many spaces it's located away from the mirror line. So beginning with point A, we count 1, 2. So since A is located 2 spaces away from the mirror line, we would go 2 spaces in the other direction. 1, 2. Therefore, in this position, point A prime would be located. And we know that we read the x values first, then the y. And so A prime is located at 1, -2. B is also 2 places away. And so we will count 2 places in the other direction. B prime would be located in that position. And this is point 4, -2. Moving on to point C, our final point, we count 1, 2, 3, 4 places away from the mirror line. And so we'll have to do the same thing on the other side. 1, 2, 3, 4. So C prime would be located in this position, which we call 4, 4, according to our graph. Then we will just connect our points. And what do you notice about the object and its image? literally by definition. It is the same as, or they are both similar, however, the image is flipped over the mirror line. Let's recap and see how some fellow students from our sister isle Barbuda engage with transformations.
Slide to the right,
That's a translation.
turn around,
That's a rotation.
flip it over.
That's a reflection. And these are all called transformations.
A flip is a reflection, a slide is a translation, a turn is a rotation. Let's turn it around. A flip is a reflection, a slide is a translation, a turn is a rotation. Let's turn it around. Let's look at one last transformation by watching this shape take on a new formation. Same shape, different size and location. The name for this is a dilation.
Thank you to the students of Sir McChesney George Secondary for sharing their wonderful transformation selection. Now let's take a look at our challenge question for week 6. Triangle ABC has coordinates A, -3, 3, B, -4, 3, and C, -1, 3. First, you're asked to translate triangle ABC using the vector 4, -2 and label the triangle A prime, B prime, C prime. Then you are asked to reflect triangle A prime, B prime, C prime in the line y equals 2 and label the triangle A double prime, B double prime, C double prime. Give the coordinates of the second image. A double prime, B double prime, C double prime. Thank you so much for tuning in to today's lesson. Remember that there are prizes to be won, so join the challenge and send your responses to mathmatters268@gmail.com. Once again, our email is mathmatters268@gmail.com. We look forward to your submissions. And join us next Monday at 5:30 when Miss Jacobs will tell us about trigonometry.
Come, take a journey with us each Monday from 5:30 p.m. on ABS TV. Let's get to the heart of the matter. Math